Torque is simply the tendency of a force to rotate an object about an axis point, usually called the fulcrum. In this picture, the fulcrum is the rock, and the man is using his hands to exert a force on the rod. To calculate the torque, we simply need to know the force that's being exerted and the distance from the force to the fulcrum. And that's your equation. Torque is simply equal to the force times the distance to the fulcrum. In this case, it looks like the man might be exerting two forces, one with both hands. If that's the case, we can combine the forces, and to find the distance, we would simply pick the middle between the two forces. Most of your torque problems will actually deal with a state called equilibrium. Equilibrium is where neither side is experiencing a net torque, or the torque provided by both sides is the same. In other words, the force times the distance on one side is going to be equal to the force times the distance on the other side. In this case, we could see on the right-hand side, we have a small weight exerting a small force. But we also have a big distance. The weight is a long ways away from the fulcrum. On the left-hand side, we have a much bigger weight exerting a much larger force, but the distance from the fulcrum is smaller. On the scale, your body is exerting a force, which in turn creates torque on the part where you read your weight. As the doctor is shifting these lead weights back and forth, they're adjusting the difference. The goal is to get the force of the lead weight times the distance from the weight of the fulcrum, and the fulcrum is this pivot point right here. The goal is to get the force times the distance equal to the torque created by your body. When the two torques are balanced, the scale will hover motionlessly on the left, and that's because there is no net torque, or the scale doesn't move. Here's a fairly standard torque problem, as we have a board hanging in equilibrium from a string. This string will act as the axis point or the fulcrum on the board. The two forces we have are the 10 kilogram weight on one side. Gravity is pulling down on the 10 kilogram weight with a force of mg, or in this case, 10 kilograms times the acceleration from gravity, which is 10, so we have 100 newtons pulling down on the left-hand side. We also have the weight of the board. And the question is, where does the weight of the board push down? In reality, it pushes down everywhere evenly along the length of the board. But if we calculate the weight of the board that way, it makes our math pretty impossible. So instead, we make up a number called the center of gravity. The center of gravity is really just the middle of the board. So we pretend all of the mass of the board pushes down in the middle of the board. Again, the mass of the board really pushes everywhere, but to make our math manageable, we pretend that it only pushes down in the middle of the board. So our board is a total of 4 meters long, and the distance from the 10 kilogram weight is 1. The center of gravity happens in the middle of the board, which means we've got 2 meters on the left and 2 meters on the right. That means the center of the board is also pushing away just 1 meter away from the fulcrum. Our standard equation of torque for an object in equilibrium is our force times our distance is equal to our force times our distance. Or in this case, the 10 kilogram weight times the acceleration of gravity times a distance of 1 meter is equal to the mass of the board times gravity, which is 10, times a distance of 1 meter. Do some algebra, and the mass of the board is also 10. Here's another problem that might seem a bit more complicated. We have a 10-meter long board with Paul and Tom on either side. Paul is 2 meters away from the fulcrum, which means Tom must be 8 meters away. The mass of the board is 20 kilograms. That's exerting a force. The mass of the board is 20 kilograms, and we pretend that that's exerting a force exactly in the middle of the board, or in this case, right at the 5-meter mark, or another 3 meters away from the fulcrum. So we have 20 kilograms times 10 for gravity, or 200 newtons pushing down in the middle of the board. The total torque from the mass of the board is simply going to be the force times the distance. So from the weight of the board, we have 200 newtons of force times a distance of 3, or 600 newtons of torque. That's from the weight of the board. Tom is also exerting torque on the board, and again, we'll use the same equation, his force times his distance. We don't know the force from Tom yet, but we do know the distance, so we could just call his force T and his distance 8. Or the total torque from Tom is simply 8T. Likewise, we could call the torque from Paul simply 2P, his force times his distance. Now here's what we know. This board is standing in equilibrium, which means there's no movement. That must mean all the torques cancel out. Or the torque we get on the left-hand side, which is 8T from Tom, plus the 600 from the weight of the board, that's going to be equal to 2P. Simplify the equation, we get 4T plus 300. The question also tells us that Paul and Tom have a combined mass of 200 kilograms, or 2,000 newtons. So we could write the equation that P plus T, again this is their force, is equal to 2,000 newtons. Now this is where we might have to freshen up our algebra skills. Subtract P from both sides, and we get Tom's force is equal to 2,000 minus Paul's force. And then we can plug that into this equation here. And then we get 8,000 minus 4P plus 300 is equal to P. Or 8,300 is equal to 5P. Divide both sides by 5 and we get P is equal to 1,660. Now normally we convert kilograms into newtons by multiplying by 10, so in this case we're going to convert from newtons back to kilograms by dividing by 10. Some zeros cancel out and we're left with Paul's mass, or 166 kilograms.